This is APAB Calculus, and we are talking about 1.1 from your textbook today, which is the section entitled What is Calculus? There's three big things we're going to address in this fairly short video, because this is a fairly short section in your book, so this shouldn't be a full class period worth of videos. So we're going to talk about what calculus is. We're going to talk about the tangent line problem, which is sort of the problem that gets us into what calculus really does and what it is. And then we're going to do an intro to limits and the limit process, because that's really what gets us to calculus. So first and foremost, let's talk about the difference between calc and pre-calc. So fundamentally, calculus is the mathematics of change. Calculus allows us to look at objects that are not moving with constant velocity. It allows us to look at problems where things are changing instantaneously, and that's something you weren't able to do in pre-calc or any of the classes before this. So as a simple example, if I gave you a car traveling at a constant speed, like a car traveling at 65 miles per hour, you would be able to use pre-calculus and maths before pre-calculus, like algebra, to talk about the way that that car is traveling and to talk about where its position will be and all sorts of other things about that car. So a very straightforward problem that you might see in like a physics class. Without calculus, you can deal with things that are moving at constant velocity. But if instead I talk about something that is accelerating, so let's say an object that you drop out of an airplane and is accelerating due to gravity, you can't actually analyze things about that without calculus. Now, you might have already been in a physics class without calculus and said, wait, no, I totally can. Well, the thing is that there are these classes called algebra-based physics classes. And what they do is they hand you the formulae that you would need to evaluate these particular objects, like an object in freefall, but they don't actually explain the math behind it, and they only work in certain situations. So to analyze any object that's moving at an inconsistent velocity, we actually need calculus. So essentially the difference between calculus, right? So the difference between calculus, it's the mathematics of change, okay? So as an example, the easiest example is that you could talk about a particle or a car or whatever you want to talk about, particle moving at a non-constant velocity, right? And you can actually figure out information about that, which you can't do without calculus. Whereas if you talk about pre-calc, and before that, right, so like algebra and everything else, right, you would have to talk about something that is moving only at a constant velocity. So in reality, so at a constant velocity. So in reality, any physics or any of this science stuff that you've done before calculus is either done with calculus knowledge handed to you, like a formula that has been created based on calculus, or you're doing some weird version of it. So for instance, if I wanted to know the velocity that a car is moving, I could do change in distance over change in time, right? And you've probably learned that since like maybe 4th grade, right? Like that's pretty straightforward science from elementary school. But the trick is that that's not actually the velocity that a car is moving, right? That would be its average velocity. So if I travel 200 miles in 4 hours, then in theory I'm averaging 50 miles per hour. But that doesn't mean I was actually always going 50 miles per hour, because maybe I had to stop at a rest area, or maybe I was totally speeding a little bit in the middle there, or maybe, I just slowed down because I saw some really pretty leaves in the fall. Who knows? But like, you really probably weren't traveling at 50 miles an hour the entire time. So again, pre-calc and algebra allow us to find things like average speed, but to find the actual instantaneous velocity of something, you need calculus. Okay, so let's talk about the tangent line problem, all right? So fundamentally, right, so let's talk about the difference between a tangent line and a secant line. So I'm going to give myself a little bit of space. So tangent line versus secant line. Okay, so in a circle, if you have a circle, right, a tangent line is a line that touches a circle once. If you have a circle, a secant line is a line that touches the circle twice. And that's just an example of so this is an example of a tangent line, right? Now, it doesn't have to be that one. It could be one up here, right? Touches it once, like glances off the edge, right? So tangent line, and this is an example of a secant line, right? So a secant line touches 2 points in a circle. Well, the same basic thing is true if we're talking about some curve, right? So let's say I have this like crazy curve that I'm going to call f of x, right? And, sorry, computer went to sleep on me for a sec. I'm going to redraw that crazy curve as best as I can. It's the problem with drawing crazy curves. Okay, so if I wanted a line tangent to, let's say, right here, like this point that I'm just going to call A, I could draw a tangent line that would look something like this. Now, it does actually intersect the curve twice, but at this moment, it is tangential to the curve. Okay, so that's a tangent line. So this is the tangent line at x equals A, right? Now, the problem is that if I wanted to write an equation for that tangent line, right, I can't, because if you think back to all of the algebra that you've done and all the pre-calc you've done, to write the equation of a line, you need two things. You need a point and a slope, but if you don't have a slope, you need 2 points to find the slope. And here, you don't know how to find the slope because you only have this 1 point. You have the point A, comma, f of A, right? So instead, what we do in all of this pre-calculus stuff is we actually don't find the slope of tangent lines. What we do is we find the slope of secant lines. So if I want the slope of this tangent line at, let's say, A, right, I would pick some other point, right, or even if you wanted to say this is some x, I would pick some other point that is h units away, meaning that this spot would be x plus h, and I would find the slope of the secant line, right, so this is a secant line, and it has the points, and again, I picked A here, but if you want, you could pick x comma f of x just to be consistent, because that's what I did over here, right? So secant line between the point x comma f of x and the point x plus h comma f of x plus h. Now, I could find the slope of this line using pre-calculus knowledge. I can't find the slope of this line using pre-calculus knowledge because I don't know 2 points, I only know 1. So the tangent line problem, essentially, the reason we need to be able to find the tangent line to a curve is that tangent line slope tells us a lot about information regarding the curve, right? So this slope of the tangent line, if you picture it like this is a roller coaster, if you were to fly off the roller coaster, if you're on some roller coaster, and way up here, at this moment, the roller coaster accidentally breaks and you go flying, you're going to fly off at a course that is tangential to that point where you fly off the roller coaster. Now, of course, because of gravity, you're actually going to do this, right? But in a situation with zero gravity, you would fly off tangentially and go forever on that tangent line, right? So a lot of the physics that we talks about tangent lines, because that's actually how things physically work. If you were swinging around in a circle and let's say you're swinging a weight around in a circle and the rope breaks right here, it's gonna this weight that you have is gonna fly off at a tangential on a tangent line. So at a tangential projection from there, essentially. So tangent lines matter a lot in physics and they matter a lot in mathematics. But again, we can't write the equation of this tangent line. So in order to do that, we're going to start by talking about how we'd write the slope of this secant line, right? So let's talk about how we could find the slope of the secant line. Because right now, again, you don't know enough to find the slope of the tangent line, but you do know enough using algebra and this picture right here to find the slope of the secant line. So this thing's slope would be, here's my y2 and my x2, and here's my y1 and my x1, right? My slope is y2 minus y1 over x2 minus x1, right? Which in this situation would be y2, which is f of x plus h, minus y1, which is f of x, all over x2, which is x plus h, minus x1, which is an h, which is an x rather. So my slope of the secant line, and I'm actually going to call it ms just for slope secant because we're gonna talk about the tangent slope in a sec. I'm going to get f of x plus h minus f of x all over h. Now this thing right here is actually a special thing that we use often enough in calculus it has a special name. So whenever you hear something called the difference quotient, they're talking about this. Now a thing about that, things in math are named either after a person or after exactly what they are. This is obviously not named after Mr. Difference Quotient, or Miss Difference Quotient. So realistically, this is called a difference quotient because it is a difference. There's subtraction on the top, that's a difference, and it's division on the bottom, a difference quotient. So subtraction and division, difference quotient. But when you put the word the in front, lots of things are difference quotients. This is the big one important difference quotient. And again, it's f of x plus h minus f of x all over h, okay? So that's the slope of my secant line. Now, if I want to find the slope of a tangent line, the reason I can't find this slope easily is because there's only the 1 point, right? I have 1 point, not 2. So essentially, what we want to do in calculus to find the slope of the tangent line is we want to move these 2 points, right? We want to move these 2 points closer and closer and closer together until they are essentially the same point. Well, there's a way that we can do that in calculus, and it's called the limit process. So what a limit is the idea of approaching a number, getting really, really close to a number, but not actually reaching it, right? So a limit is the idea of, so it is the output when you get infinitely close. That's not how you spell any of that. Infinitely close to some x value, right? Or some, we can even say some input value because it's not always x. Okay, so essentially it's the output when you get infinitely close to some value. Specifically in this case, what we want to do is we want to have this h value get really, really, really close to 0, right? Since we want these 2 points to get so close together, they are fundamentally the same point. What we're going to do is we're going to say we want h to get really, 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 really close to 0. So what we're going to want is we're going to want the tangent slope, I'm going to call it m sub t, to be the limit as h gets really close to 0 of this difference quotient, right, of this thing that we saw. This thing right here, this tangent slope, is actually also called the derivative of f of x, and we write it as f prime of x. And we're going to spend time working on that over the next, most of this course. We're going to spend a lot of time doing differential calculus, which means taking the derivative or finding the derivative of a function. But that tangent slope essentially is what we get as we make this h get smaller and smaller and smaller and smaller and smaller until the points are so close together that they are the same point, even though officially you need 2 points to find the slope of these things. So if we walk through an example, just to show you what I mean by finding the slope of a secant line. So let's walk through a quick example of this. And then we're going to spend a lot of time on limits for the rest of this chapter. So let's walk through an example. All right. All right, so I'm going to pick a curve that we're all probably pretty familiar with. I'm going to pick x squared, okay? And I'm going to use secant lines to approximate the slope of the tangent line. Line at, let's do x equals 2. Okay, so here's the idea. I want to approximate the slope of the tangent line at x is 2. So if we think about what this graph looks like, right? 0, 0, 1, 1, 2 squared is 4, 3 squared is 9. Okay, so here's the half of this thing that I'm worried about. There's another half to the parabola too, but I'm looking at this half. Okay, terrible at drawing graphs, but it's okay. All right, so I'm trying to approximate the tangent slope right here, right? That's what I want. I want the tangent slope at the point 2, 4, right? But I can't get that tangent slope with just 1 point, right? So I want the tangent slope at 2, 4. So I'm going to progressively pick points closer and closer together and show you how we're going to find the slope of this thing. And I can tell you right now that we can find the actual slope, and I'll give you the actual slope in a sec, but let's walk through. So for A, I'm going to use the point I want, which is 2, 4, and let's use a point that is 1 full unit away, so 3, 9, right? Because 3 squared is 9. So just to be clear, that means, so h was 1, right? To get from 2 to 3, it was 2 plus 1 gives me 3, right? So my secant slope would be y minus the y value over x minus the x value, right? So I get 5 over 1, which is a slope of 5, right? Now, if I get slightly closer together, I should get a slightly better estimate, right? So now, instead of using 2, 4, and 3, 9, I'm going to use 2, 4, and I'll use 2.5, right? comma 6.25, right? Because that's what 2.5 squared should be, I believe. Yes. Okay. So now my secant slope, which should be slightly better, like this is a slightly more accurate representation, my secant slope should now be y minus the y value over my x minus the x value, right? So I get 2.25 divided by 0.5, which should be a 4.5. Okay, it's a slightly more accurate slope. And as I get closer and closer, I should get more and more accurate slopes, right? So I'm going to use something pretty close together now. I'm going to use 2 comma 4, and then I'm going to pick, let's use 2.1. Sometimes my brain completely breaks, and I don't feel like doing 2.1 quantity squared. Cool. So this is a 4.41, which I should have been able to come up with. But hey, every once in a while we don't have a brain that works. So I'm going to get y minus the y value over x minus the x value, right? We get 0.41 divided by 0.1, which is going to be a 4.1. Okay, so notice, if you look at these slopes, they're getting closer and closer to the number 4, seemingly, and that is the right answer. So I'm going to show you, so if I do a little bit closer, so again, what I'm doing is I'm taking, this is the point I want, and I'm picking a point that is closer and closer, right? So just to be clear, my h here was 0.5, my h here was 0.1, right? See how the h's are getting smaller, right? Like the value between the two x's is getting smaller. So let's pick an even smaller one. Let's do 2 comma 4, and let's do 2.01 comma, I don't really feel like doing that, so I'm just going to go ahead and type it in a calculator because I'm a lazy bum. So that's 4.0401, very small. Okay, so now my secant slope would be y minus the y value, so 4.0401 minus 4 over 2.01 minus 2. So that's a 0.0401 divided by 0.01, and I get 4.01. You can see how close that's getting to 4. So I'm going to go ahead and tell you that using calculus that you don't know yet, right? So using calc, which is a spoiler because you don't know it yet, right? So using calc, I can tell you that this tangent slope is definitely a 4. And what you'll notice is, as the points got closer and closer together, my approximation of that tangent slope got closer and closer to 4, okay? So we're going to learn how to do this as we move forward, but the idea is that the secant slope, right? The secant slope is an approximation for the tangent slope, which is the instantaneous slope of a nonlinear curve, right? The problem with this is it's not a line, and usually when you talk about slopes in algebra or pre-calc, you're talking about lines, and this is nonlinear. But you're able to find the slope of a curve. You can find the slope of any curve at any point using calculus, and that's what we found here, essentially. So this is the slope of the curve, f of x equals x squared at x equals 2, right? So the tangent line, right? And one way to write that, and we're going to talk about this as we get closer, the other way to write this, like as we move further on, is f prime of 2 is a 4. And we're going to learn how to deal with that notation and what it means as we move forward. But that's kind of the idea. So these are secant lines where I move the points closer and closer to that 2 comma 4, right? So here my h was 0.01. It was really small, and you can see how close the slope got to the value I actually wanted. So there is a second half of calculus that I did forget to mention in the intro that we'll just talk about for a sec. So basically, calculus breaks down into 2 halves. Calc 1 that you're going to learn breaks down into 2 halves. Differential calculus, which is essentially finding the slopes, finding the slope of a curve, right? Differentiating is finding the tangent slope of a curve. And integration, which is finding the area under a curve. So the other half of calculus, right? So this is the first half of the calc that you're going to learn. The other half of calculus is going to talk about approximating area under curves. So in the second half of this course, usually sometime around winter vacation, we're going to talk about integral calculus, which is finding the area under curves. So essentially, calculus breaks down into 2 big categories. Differential calculus, where we find the slope of tangent lines, which is called a derivative. That's not how you spell that. Derivative. Okay. And then integral calculus, where we find the area under curves. Okay, and that's called integration. So we integrate. So essentially that's the two categories of calculus, and we're going to talk a lot more about this. So this is basically September until around December, and this is December until around March, and then we go ahead and start studying for the AP. Okay, so that's sort of what we're looking at, and you're going to learn in the second half of this course how to find area under curves, which is the other thing calculus lets us do. So, so for instance, if I asked you to find the area under this curve, right? Let's say this is my curve, and I asked you to find this area right here, right? You could find this because you could use geometry to find this area because it's just a triangle, right? But if I gave you a curve like this, and I asked you to find this area, you absolutely could not do that accurately with geometry, and you would need calculus. So essentially, what Calc does is it opens up a whole bunch of doors that have previously been closed, because you're going to be able to do a lot of skills that just can't exist without this math of change. So anyway, that's our 1.1, and we're going to go ahead and start talking about how to use limits and what the notation means in our next video. That'll be 1.2.